The Earth is not unique. In the last few years, scientists have discovered that our planet is just one of billions in the Milky Way galaxy.
There's a really decent chance that there are more planets in the galaxy than there actually are stars.
These planets are now being scrutinized for evidence of atmospheres, liquid water, and perhaps even life itself.
We have a scientific method to actually determine whether there is life on another planet.
Another Earth. Alien life. The truth lies beyond our skies, but are we prepared for it?
On Earth, all life requires liquid water to grow and reproduce. It's the common ecological requirement for life.
Liquid water is just so good for getting evolution going. Molecules can dissolve in the water, actually interact with each other, form more complex chains. Now that's very rare. Hardly any other liquids do that. So liquid water is a natural starting place when you look out into the universe and say, what planets could possibly have life?
To gauge how much liquid water is in space, astronomers had to first calculate how common water is in all its forms. Amazingly, it's found wherever they look.
Water is incredibly common. In its gaseous form, we see water vapor filling the space between the stars. We see it in clouds of material that are actually forming new stars and planets right now.
Since water is a fundamental building block of stars and planets, then it seems logical that exoplanets must have it in abundance. But if searching for life, liquid water needs to be found, and plenty of it. To find it, astronomers took inspiration from a fairy tale.
Everybody knows the famous story of Goldilocks and the Three Bears and the cup of porridge, where one was too hot, one was too cold, one was just right. When it comes to cooking up life like a porridge, you need to have an environment that's not too hot, not too cold, just right. And traditionally, we look for that at a certain distance around a star.
At first, astronomers based this magical distance, known as the Goldilocks zone, on the Earth's orbit around the Sun. But as they've found more and more exoplanets, they've had to reevaluate the limits where liquid water can exist.
There isn't a single distance. It depends on the brightness of your parent star. A dim star, you need to be closer. A hot star, very bright, you need to be farther away.
But if the planet's atmospheres are rich with greenhouse gases, then they can still have liquid water even outside the habitable zone.
You could have an atmosphere rich in carbon dioxide that has a strong natural greenhouse effect, and that means the planet could be much farther out of the Goldilocks zone, but there could still be liquid water because of the composition of the atmosphere.
And planets orbiting much closer to their stars can avoid overheating if their surface is pale and highly reflective.
When we search for habitable zones, we have to be careful to understand what we're really looking for.
Scientists have calculated how many rocky planets may lie within the Goldilocks zone of their stars. And it's over 30 billion potentially watery worlds. Even more remarkably, recent discoveries have shown that it's not just planets that can exist in the Goldilocks zone. There may be moons too, awash with oceans.
Most of the planets we're finding are big Jupiter-sized planets. However, a lot of them are orbiting roughly where the Earth is orbiting the Sun. So even if the planet that we're finding can't support life, it could have a moon with an atmosphere that could support life.
And the biggest of these moons may be similar to Earth.
There could be billions upon billions of exomoons out there, and even perhaps countless paradises teeming with life.
David Kipping searches for exomoons by looking for double dips in the brightness of distant stars.
We look for exomoons in a very similar way to the way that we look for planets, by looking for them transit their host star. Now, if that planet had a moon, then we should expect to have one big dip due to the planet, and then one smaller dip either to the left or to the right due to the moon.
And some of these habitable exomoons may have some of the most spectacular sights in the universe. Imagine a warm, rocky world similar to Earth, with oceans and mountains. But in the sky, there's a massive ringed planet and another moon that's ejecting hot magma into space. Exoplanets, along with exomoons, hint at a galaxy filled with the possibilities for life. But for life, a rocky planet and liquid ocean may not be enough. Biology requires something else: air. As the sun's light falls on Earth, a halo appears, a pale blue ring of light, our atmosphere, and without it, we wouldn't be here. The Earth's atmosphere provides the gases that fuel the biochemistry of advanced life. But it also protects the oceans from the full ferocity of the sun's rays, preventing the water from boiling away into space. Without an atmosphere, there would be no wind, no rain, no fresh water, and no life.
Atmospheres are absolutely essential for life. Take a look at the planet Earth, and you realize that just like the skin of the apple preserves the apple, well, the atmosphere of our planet preserves the oceans and makes possible the presence of...
The challenge is that these planets are very small and very faint. So we can't actually go and directly measure the light emitted from the planet the same way that we go and measure this lovely spectrum for the sun. Instead, we have to rely on more indirect methods. So one indirect way of doing that is to wait until the planet passes in front of the star.
When the light of a star passes through an exoplanet's atmosphere, the gases that surround the planet should cast their own faint lines on the star's spectrum.
So as we watch the light from the star transmitted through that atmosphere, its atmosphere is going to act like a little filter. So part of the starlight's going to pass through that atmosphere, and we're going to see that imprinting extra lines on it, which are due to the planet's atmosphere. So that change in the spectrum tells us something about the properties of the planet's atmosphere.
And trying to take direct photographs of exoplanets using massive, ground-based telescopes.
Awaiting instructions.
We're within minutes of taking our first long exposure, and I hope it's good.
The toughest aspect of photographing exoplanets is the blinding light of the parent star, which shines tens of millions of times brighter than the planet itself. The key is to stop the light of the star entering the telescope's sensors by blocking it, achieved by using a series of masks and lenses called a coronagraph.
Right now we're standing right underneath the telescope's primary mirror, and the light comes through a hole in the middle of the mirror and goes into this crazy box here, which is full of optics, motors, sensors, and electronics that all allow us to precisely control the starlight that's coming through the system.
Software is then used to manipulate the coronagraph to block out the unwanted sunlight.
Under good conditions, we can actually carve dark holes into this image of the star so that we can see really faint things in those regions.
But coronagraphs produce an intriguing problem. Errors within the optics produce tiny flares of starlight called speckles, which appear just like exoplanets. However, Ben has developed an ingenious way to distinguish the planets from the speckles.
So we've developed a technique where we exploit an aspect of speckles, which is that they change position in the image depending on what color you take your image at.
Image processing.
Ben takes the same image of the star through different color filters and runs them like a movie. The speckles appear to move across the screen. However, the planets don't, allowing Ben to easily identify them.
And so I'd like to point out that there is a little thing right here that if you watch, you're careful, you'll notice that it doesn't move and the speckles are washing over it.
This stationary blob is a candidate exoplanet, and below it to the left is a second. They both appear to orbit a star that's about 200 light-years from the Earth. Just a decade ago, capturing an image such as this through a telescope was unthinkable.
Studying much larger planets, gaseous things like Jupiter that most likely don't have any kind of life like we know it, but that's a first step. And we're going to fainter and smaller planets as time goes on as we develop this technology.
In the not-too-distant future, scientists may be able to simply scan a star for Earth-like planets and find it has the biosignature of life.
We can look right at the light from a little planet around its distant star, and that opens up a whole range of possibilities for us to not just detect the planet, but to study the planet.
I mean, this all sounds like science fiction, but there is a reality to this. We have a scientific method to actually determine whether there is life on another planet.
Life is one thing, but life that's intelligent is another altogether. It requires billions of years of evolution and a powerful force field, similar to that which we owe our lives to every day. If somebody from outside our solar system were to study it, they may well make a surprising observation. Of the 8 planets that orbit our Sun, they might calculate that 2, not 1, is suitable for life. And this would be because the Sun has 2 planets orbiting within its Goldilocks zone, the Earth and Mars. Both planets have surfaces warm enough for liquid water to pool on. Yet, while the Earth is blessed with warm oceans, Mars is dry and dead. There is one crucial difference between the 2 planets, and it could be the key to finding habitable exoplanets: a magnetic field. Our Sun is constantly emitting deadly radiation out towards Earth. And we're only protected because of our magnetic field, or magnetosphere. Without it, the solar wind would blow our atmosphere away, and without an atmosphere, liquid water couldn't exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. You know, if there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
So where does Earth's magnetosphere come from? And why doesn't Mars have one? Actually, in the past, both Earth and Mars had magnetospheres. However, Mars lost its around 4 billion years ago, and along with it, the potential for life to develop. Earth and Mars were created during a period of violence. Asteroids smashed into their surfaces, turning rock and metal into a molten mass. As they started to cool, a solid crust formed on the surface. But the molten metal below churned as the planets turned, inducing a magnetic field, which rose high up above the surface of both planets. Active volcanoes expelled gas into the space around each planet. Protected by the newly formed magnetic field, these gases built up into thick atmospheres, creating the air pressure for liquid water to run on the surface. For over 100 million years, both Mars and Earth were warm, wet paradises, ready for life to evolve. Then Mars's magnetic protection suddenly disappeared. The solar wind blew its atmosphere into space. Then its oceans boiled away, leaving the dry, sterile red rock we know today.
Mars's fundamental problem is that it's smaller than Earth. And because it's smaller, the internal core of Mars cooled down and solidified. And once it becomes a solid metal, there's no more magnetic field. The magnetic field shuts off, essentially, and the atmosphere, therefore, is vulnerable to both energy and radiation from the sun and the rest of the galaxy, and probably just blew off. Whatever life was on there, at least on the surface, is now completely exposed.
All rocky planets will eventually lose their magnetospheres as their cores cool and turn solid. So one way to find out if an exoplanet is alive is to discover if its magnetosphere is still active. Yet magnetospheres are difficult to measure because they're incredibly weak.
The Earth has a magnetic field of approximately half a Gauss, which, when you think about it, is actually really weak. Our fridge magnets are about 100 Gauss, so they're much stronger.
Exoplanets are far too far away for these weak magnetic fields to be measured directly. But there is an indirect method. when electrons in the solar wind interact with the planet's magnetosphere, they emit radio waves that beam out into space. It turns the planet into a giant radio beacon. Astronomers such as Evgenia hope to use these signals to detect habitable exoplanets. Not only that, the frequency of the signal should also indicate how big the planet is.
If we're looking for the magnetic signature in the radio waves of a giant planet, say a hot Jupiter, we expect it to have a strong magnetic field, and therefore it would have a high frequency, and around 100 megahertz, kind of where the limit of this radio is. However, a weaker field like Earth's requires us to go down to lower and lower frequencies. So instead of 100 megahertz, we go down to 10 megahertz.
But looking for exoplanets at 10 megahertz presents a unique challenge, because the Earth's own magnetosphere generates a signal that interferes with this search. So to find other Earths using radio requires a dish in space.
When we want to look for magnetospheres of extrasolar planets, we really need to get outside of the Earth-Moon system in order to get away from all the radio frequencies that are bouncing around the Earth.
With the development of new techniques and technologies, scientists are edging closer to finding a second Earth.
I wouldn't be surprised if we have that data about an Earth and about life on it around another star in 10 or 15 years. I'm hoping to see that soon.
Using shadows, light spectrums, and now radio, scientists have the tools to detect a planet similar to our own. But in the rush to find a planet like Earth, are we missing something? What if Earth isn't habitability? Is there another sort of planet that's even better for life to evolve? For years, astronomers have scanned the skies for planets that could sustain life. They've based their search on the Earth, seeking the exact same conditions and the exact same size.
I think right now there's a huge focus to finding Earth-like planets. Now, whether or not there actually is life there, that is another question altogether.
But after 20 years of searching for another Earth, the scientists may be about to change their focus. Recent observations have revealed a brand new class of planet, one that may eclipse our own. Astronomers call this mysterious new class of planets super-Earths.
Super-Earths are about 3 to 5 times the mass of the Earth, and there's nothing like that here. We don't know what they're like. It's an entirely alien sort of planet.
In recent years, astronomers have begun to imagine the conditions on this new class of planet, and they've come to a startling conclusion. Super-Earths could be even more habitable.
There are probably planets out there that are even more hospitable for life. Planets that have even more chemicals necessary to create the organic materials that create life, conditions that make it more likely to get life off the ground.
Imagine a rocky planet twice the size of the Earth, with volcanism on the surface that indicates a vast source of heat and magma within its core.
We expect that a heavier Earth will be more geologically active, that the increased amount of geothermal heat within the super-Earth will lead to stronger motions of the magma underneath the crust.
Erupting volcanoes dot the surface of this super-Earth. Their gases feed a super-thick atmosphere, and help to regulate a super-stable climate.
Many times, life on Earth was nearly extinguished. For example, once upon a time, the Earth was snowball Earth, completely covered in ice. Maybe in these other planets, there are Earths in which snowball Earth never happened, that the climate was always stable and temperate.
Gravity is 3 times stronger here than on our planet. It pulls mountain ranges down to 1/3 of the height they'd be on Earth. Gravity also flattens the ocean bed, creating shallower seas, filled with volcanic island chains. And the nutrient-rich waters that surround these archipelagos provide the perfect conditions for life.
In these other planets, perhaps they have conditions which would make DNA get off the ground much earlier and flourish much more quickly.
Finally, the super-Earth may be protected by a super magnetosphere.
The magnetic field strength is a condition both of the mass of the planet as well as its rotation speed. And so it is quite likely that a planet that is a couple of times bigger than the Earth's would be able to develop a stronger magnetic field, may shield the planet even better than our magnetic field shields us.
Having a stronger magnetosphere would be advantageous for life on a super-Earth if it were orbiting the Milky Way's most abundant type of star, the M dwarf or red dwarf star. Red dwarf habitable zones are much closer in because their host star is so dim.
It's as if you took the terrestrial planets in our own solar system and zapped it with a shrink ray gun and shrunk them down to orbital periods that are less than about 30 days, meaning that they're very close to their stars.
Some astronomers believe this puts these planets at risk from solar activity, such as deadly flares. But a super-Earth with a super-protective magnetosphere may well deflect these deadly rays, allowing life to flourish under a sky full of stunning auroras.
If one was standing on a super-Earth, we would see the aurorae come down to lower latitudes. You might get different colors. If I had the opportunity to travel to one of these exoplanets, I would snap that up pretty quickly.
Most intriguing of all, if life does exist on a red dwarf super-Earth, it could be home to the oldest civilizations in the entire universe.
The advantage of the M dwarfs is that they last for much longer. And if you had a super-Earth then, keeping a strong magnetic field, going for billions and billions of years, especially now around a red dwarf that is going to exist for billions and billions of years. You might be in that perfect system where life can exist and evolve into even more complex beings than us.
And in among the stars near to us, red dwarfs are abundant, bursting with the potential for advanced life. But in our galaxy, there are also cosmic events that can destroy life on a regular basis. So is there anywhere that is safe? The hunt for exoplanets is well underway. The Kepler Space Telescope has scanned the stars near to us for planets and has found them by the thousands.
For a long time, we didn't know if the other stars in our galaxy had planets. And for thousands of years, there was no way to answer that question. Finally, now with modern technology, we can do that. And to our surprise, we found they are extremely common.
From Kepler's small sample, astronomers believe there could be tens of billions of rocky Earth-like planets throughout the Milky Way, where life may already be thriving. how many of these countless worlds have held on to this life long enough for intelligence to evolve? The answer may depend on a planet's position in space.
The universe is not a happy, safe place. The universe wants to kill us. It's incredibly violent out there. There are solar flares and supernovae and black holes and colliding galaxies and all these really amazingly dangerous and violent events. It's actually kind of amazing that we're here at all.
In order to develop advanced, intelligent life, an exoplanet may have to avoid these cosmic violent events for over 3 billion years.
If we look at the history of the Earth, the first thing that happens that's important is the origin of life, right away, very quickly. But then, nothing for a long time. You have nothing but microbes stomping on the Earth.
Single-celled microbes ruled the Earth for 2.5 billion years. Multicellular life has only been around for 1 billion years. Fish for 500 million, mammals for 200 million. And modern humans have only walked the Earth for the last 200,000 years. It's clear that it takes a long time for intelligent life to develop. But most planets in the Milky Way aren't afforded this amount of time. Astronomers believe that a planet's position within a galaxy may determine whether it'll experience mass global extinction events.
There's an idea of a habitable zone for a galaxy, and it's in analogy to the habitable zone around stars.
Stars too close to the galactic center are in the direct line of their violent neighbors, which frequently blast them with deadly high-energy radiation.
In the middle of a galaxy, we have a lot of bright stars and young stars and maybe even supernova going off. And so there's a very harsh radiation field. That's not good for life.
Generated by the supermassive black hole that sits at the center of the Milky Way, this cosmic destruction area stretches out around 8,000 light-years from the galactic center and extends out along the densely packed spiral arms. Any planets that exist within this zone are likely to have life regularly obliterated from their surface. Fortunately for us, our star, the Sun, sits in a relatively empty, quiet zone between two of the galaxy's spiral arms.
So there's this idea that there's a band in the middle of the galaxy that's the galactic habitable zone, where you don't have too many stars going off, you don't have too many supernovae, so it's quiet in that way. Those might be great places for complex life.
These green zones are the quiet areas of our Milky Way galaxy. They're sheltered from the worst of the galaxy's radiation. It's these zones where Earth-like planets would experience long, uninterrupted periods of time, where life could take hold, to develop into more complex forms, and eventually, possibly, into intelligent life like us, or even superior to us. The galactic habitable zone is no more than a fledgling theory. If it's true, it reduces the number of places where advanced life could flourish in the Milky Way. However, it does mean that the places where advanced life could be should be near to us, which means that aliens are likely to be close by too. And with our technology getting better every day, it surely won't be long before we find them.
I think in 20 years' time, I'm going to be able to look up into the night sky and say there really is another place I could stand like this and feel at home.
To have cousins that we one day may communicate with seems to me to be potentially one of the greatest developments that humanity will ever experience. And if that isn't worth doing, I don't know what is.